Okay, hi everyone. So we are going to discuss the paper 2 of the SPM apps part 1. Okay, so this is the part 1 question. I'm going to do the whole paper and then of course you can decide how fast or how slow you want to go in this video. Okay, so let's begin with question 1. Diagram 1 shows two different weighing scales, X and Y. Okay, so you have an analog scale on the left and then the electronic on the right. So the question is, what is the physical quantity that can be measured by the weighing scales? Of course, the physical quantity, okay, you're talking about mass. Okay, and I think it's very important to differentiate between if the question asks what is the physical quantity as opposed to what is the type of physical quantity. So the type of physical quantity will be base quantity, derived quantity, or scalar vector quantity. That's type. Okay, that's categorizing. But the question is asking what is the physical quantity. Okay, so please be careful not to use derived or base quantity. Okay, so the physical quantity we're talking about here is mass. And I think a very common mistake is if you put weight as your answer, this is obviously a wrong answer because weight is not measured in kilograms or grams. Okay, weight is measured in newtons. Okay, if you look at this one over here, it's very clearly shown that it is in grams. Okay, so you want to make sure that you avoid this kind of mistake. Okay, state the accuracy of weighing scale Y. Okay, the accuracy is what is the smallest possible number that you can get on the weighing scale. So the answer will be 0.01 gram. Don't forget to put the units. Based on diagram 1, which of the weighing scales is more sensitive? Of course, is Y lah. Okay, Y is more sensitive. And usually when we talk about sensitivity, this always comes together. Something that is more sensitive, okay, is able to detect smaller changes. That's what it means, okay? It can tell the difference between 0.01 and 0.02, whereas the weighing scale X over here can't tell you that. Okay, so this is what we call a small change. So usually when we see the word sensitive, okay, we want to think of this sentence. It is able to detect small changes. Okay, this is kind of like the pair. When we talk about sensitive, this is the answer. Okay, diagram 2 shows a car with a mass of 3,500 kilograms. Okay, you're given the mass over here, which is stationary on a hill, okay, before it is moving down. So the question is, state the energy change when the car moves from the hill to point A. So of course, from on the hill, okay, this will be potential energy, gravitational potential energy. And then as it moves down, it's going to go into kinetic energy. Okay, so the answer will be gravitational potential energy change to kinetic energy. Okay, now calculate the gravitational potential energy. So interesting, the question already sort of give you the answer. Gravitational potential energy is mgh. Okay, you have the mass of 3,500. G, of course, is 9.81, and then the H is given as 25 meters. Okay, this will give you 34360 joules. Okay, then calculate the velocity of the car at point A. So, since we are talking about gravitational potential energy changing to kinetic energy, so we need to remember that the gravitational potential energy is equals to kinetic energy. Okay, and you already calculated the gravitational potential energy, which is 34360 equals to half mv squared. Okay, which is the formula for kinetic energy. So half times 3,500 times v squared. Okay, of course, shift everything across. Don't forget to square root, and you will get v equals to 4.43 meters per second. Okay, so then after that, you can that's basically it. So always don't forget whenever we talk about energy, okay, we always tend to use this one. Okay, one energy equals to another because the principle that we're following is the principle of conservation of energy. Okay, the principle of conservation of energy is the reason why we are doing this lah. Okay, let's move on to question 3. So diagram 3 shows a laser emitting red light in a laboratory. So what is the meaning of quantum energy? Quantum energy is discrete. Okay, discrete packets of energy with no mass. Okay, of course, the most important word is this, like discrete packets of energy lah. The word with no mass, not necessarily important lah, okay, to be there. Okay, now if the wavelength of the red light is 700 nanometers, okay, I want to point out that 700 nanometers is 700 times 10 to the power negative 9. Okay, very, very common. Determine its photon energy. So of course, photon energy, we know there are two formulas to this. It's either E equals to HF or E equals to HC over lambda. Now, the question is given wavelength. Okay, so we use the second formula for this lah. So the photon energy will be H is 6.63 times 10 negative 34. Okay, C of course is 3 times 10 to the power 8 over, don't forget to change the nanometers to times 10 to the power negative 9. Okay, it's a very straightforward formula to use. Just make sure you don't forget how to change nanometers into 10 to the power negative 9. You get 2.841 times 10 to the power negative 19 joules. Okay. Now, a red light bulb with a power of 50 watts has the same wavelength as the laser in diagram 3. Okay, so determine the number of photons per second, okay, for the light from the light bulb. Okay, so when you're given power and you're given energy and then you want to determine the number of photons, the formula is P equals to N times E. P for power and E, of course, is for energy. N is the number of electrons per second, number of photons, sorry, per second. Okay, so if we substitute, we get 50 equals to N times 2.84 times 10 to the power negative 19. Okay, it's a very, very, very straightforward formula to use. You will get N equals to 1.76 times 10 to the power negative, 10 to the power 20 photons, okay, per second. So usually, because it's number of photons per second, it's already given here, number of photons per second, okay, which is the letter N. Okay, usually we don't really have to put a unit for this, okay, but I've seen a lot of books, they usually like to put per second. Okay, so as to complete this one with the units. You can use to do that also. Okay, so 1.76 times 10 to the power 20 photons per second. Okay, so the per second unit is optional, but if you know it, why not? Okay, just put it in. All right, number 4. Diagram 4 shows the paths of 3 radioactive emissions in an electric field. Okay, so you have the negative electric field up here, the positive one down here. Okay, so name the radioactive emission H. So H is going towards the positive. Okay, so the radioactive emission will be a beta particle. Okay, or a fast-moving electron. Okay, either one of this is totally fine. So why does the pattern of the path of the radioactive emission, okay, H curve downward? Okay, because the radioactive emission is negatively charged, which is the beta particle. Okay, that's why it's going towards the positive. So the F curve upwards because the radioactive emission, okay, taken from the words over here, okay, is positively charged. Okay, the words in blue are the answers that we're looking for, but if you just for the sake of our revision okay, remember that the negatively charged radioactive emission is the beta particle. okay, or a fast-moving electron lah. The positive one, okay, is the alpha particle, okay, otherwise known as the helium-42. Okay, just for our revision. So G moves in a straight line. Why? Because it is no charge. Okay, so the radioactive emission has no charge. Okay, that's how we will answer this question. Okay, so in a nuclear reactor, uranium-235 is bombarded, etc., etc., etc. Okay, so you notice that there's an X over here and there's a Y over here. Probably we're going to use that to this one. Okay, and probably, the next question will be, what are the values of X and Y? Okay, so let's take a look. So if the values of X and Y can be determined by making sure the left and the right side are the same number. So over here on the left side, 235 plus 1 is 236. Okay, 92 plus 0 will be 92. Okay, at the top over here, it will be X plus 94 plus 2 times 1. Okay, so X plus 94 plus 2 times 1 is 2. Okay, equals to 236. So you get X equals to 143. Okay, and you do the same thing with the bottom part lah. Okay, hold on, let me write this off first. Okay, we do the bottom part, the 92, okay, is equals to 54 plus Y plus 2 times 0. 2 times 0 is still 0 lah. Okay, so 92 equals to 54 plus Y. And you get Y equals to 38. Okay, so that will be our answer. So X is 143, Y is 38. Now, the nuclear reaction above experiences a mass defect, okay, of 0.198 U. Calculate the nuclear energy. Okay, so nuclear energy is E equals to mc squared. But don't forget that the M is the mass defect in kilograms. So the first thing you have to do is change the 0.198 to kilograms, which is 0.198 times 1.66 times 10 to the power negative 27. Okay, you just multiply it by that and you will get, so the mass defect will be equals to 3.2868 times 10 to the power of negative 28 kilograms. Then only you substitute into the E equals to mc squared. Okay, so you get E equals to M is 3.2868 times 10 negative 28 times 3 times 10 to the power 8, the whole thing squared. Okay, you get 2.958 times 10 to the power negative 11 joules. Okay, roughly like that lah. Okay, number 5. Diagram 5.1a shows a light traveling from air into a diamond block. 5.1b from air into the glass block. Okay, so of course, name the phenomena of light. This is very obvious. This is refraction. How you know? Because it is the bending of light waves. Okay, so whenever the light wave change direction, it is usually, no, it's not usually, it is always, okay, a refraction. Okay, so question is, if the speed of light in the diamond, so this is diamond and this is glass. Okay, calculate the refractive indices of diamond and glass block. So there are two parts to this. You have to calculate the refractive index of the diamond and the refractive index of the glass block. Okay, so if you're going to calculate the refractive index, okay, by using the speed of light, remember, of course, you have to hold on to the fact that the speed of light in the air, okay, is always 3 times 10 to the power 8. Okay, this is in the air. So when you want to calculate refractive indices, always remember that the bigger number must be on top, okay? And the smaller number must be at the bottom. Whenever you have to count index, refractive index, even if you use angle or if you use or if you use density, you have to put the bigger number on top, because refractive index, there's no refractive index that is smaller than 1. Okay, 1 is the smallest refractive index, which is the air. That's why you always have to put the bigger number on top. So for diamond, Okay, the bigger number will be 3 times 10 to the power 8 over 1.25 times 10 to the power 8. Okay, which will give you 2.4. And remember, refractive index got no unit. Okay, for glass, same thing. Speed of light in the air must be on top. Okay, the bigger number must be on top. So 3 times 10 to the power 8 over 2 times 10 to the power of 8, 2.0 lah. Okay, which will give you 1.5. Again, no units. Okay, again, everybody notice that refractive index, the number must be always bigger than 1. Kalau kamu buat pengiraan and the number of the refractive index is smaller than 1, then know that you have probably terbalik it lah. Okay, so just to remind you lah, okay, if you're counting refractive index, okay, let me see if I find space now. Okay, refractive index is speed of light in the air over speed of light in medium. Okay, that's one way of calculating. Another way of calculating, of course, is n equals to sine I over sine R. But there is a syarat untuk ini ya. The syarat is I must be bigger than R. Okay, the condition is that I must always be bigger than R in order for you to use this formula. Okay, okay, let's move on. So, from your answer in 5B1, find the values of R. Okay, so let's bear in mind first that the refractive index for diamond is 2.4 and the refractive index for glass is 1.5. Okay, let's bear that in mind first. So if you want to find the values of R, notice that the I, okay, the incident angle, sorry, the incident angle, which is I, is 58 for both. Okay, so the formula, of course, is n equals to sine I over sine R. Okay, so let's consider diamond first lah. So for diamond will be 2.4 equals to sine 58 over sine R. Okay, sine 58 over sine R. So of course, this needs to be very carefully calculated. First, you find sine 58 or you transfer it first lah. So sine R equals to sine 58 over 2.4. Okay, now when you calculate this, make sure that you calculate it separately. Sine 58 first. Oh, sorry. Okay, sine 58. Then only you divide by 2.4. Okay, so you get 0.3533. Okay, so sine R is 0.35335, etc., etc. Then only you shift sign. Okay, I noticed that there are quite a lot of people who will still make this kind of mistakes. So R is 20.69 degrees. Okay, so be very careful when you're doing this. Because of this particular button in the calculator, okay, a lot of people tend to misuse this. They will type sine 58 over 2.4 like this. Okay, it's not correct lah. Okay, please be very careful. Let me check. Okay, you get a totally different value. You get 0.4093. Okay, so be very careful when you're doing this lah. Okay, because the calculator is meant to help you, not to replace you. So please make sure that even when you're using calculator, tolong guna otak. Okay, please use your brains when you're using calculator. Do the divide first and then only shift sign. Okay, so that's for diamond. Now for glass is the same thing. Okay, 1.5 equals to sine 58 over sine R. Okay, so you shift it around, you do everything in the same way, you get R equals to 34.43 degrees. Okay, which is the answer. So notice that after that, they will ask you to find the relationship between the refractive index N and the speed of light in the medium V. Okay, so if you take a look, the speed of light for diamond is 1.25, but the refractive index is bigger. The speed of light in glass is bigger, but the refractive index is smaller. So obviously it will be two different, one up, one down. So the bigger the refractive index, the smaller the speed of light in the medium. Okay, just to remind you that for writing the relationship, whenever you write the relationship, please avoid using words like inversely proportional or directly proportional because you are talking about values. There is no graph here. Okay, when you talk about directly proportional, inversely proportional, you're referring to a relationship based on the graph. But in our situation over here, kita tengok value. We're looking at the numbers, we're looking at the values. So you shouldn't be using the words inversely proportional or directly proportional, okay? Unless it is a law. Unless it is a law, if it is a definition that has the word inversely or directly proportional, then you got no choice lah. But if they're asking you to write a relationship based on your calculation, everything, please don't use words like inversely, directly proportional, okay? Because it's a technical error lah. Okay, be very careful with that. Okay, diagram 5.2 shows an observer observing the image of a fish in the water. Okay, so on diagram 5.2, should draw two rays of light to determine the actual position of the fish. Okay, so the first thing that we need to know is that in refraction, this is the image that he's seeing. Okay, so if it's the image, remember that the light travels in a straight line. So you want to draw a straight line from the eye all the way to the fish. Okay, so I'm going to use that as a base. Okay, so then of course, where the air and the water is, you draw a normal line. Okay, and then remember that since the light is traveling this way, it has to refract from somewhere. Okay, so we usually draw a second line over here, the actual position of the fish. Okay, then after that, you can draw. Sorry, I'm just going to draw a fake fish. Okay, so the fish should be somewhere like this. Okay, so this is the first ray, and then this is the second ray. And then, of course, the third mark is this one to show how you actually saw the image in the first place. Okay, so be very, very careful with this. This is a very common drawing for refraction. Okay, remember that the eye to the image is always a straight line. Okay, so the eye to image, okay, is a straight line. Okay, manakala the eye to the object, the actual object okay, is refracted line. Refracted light ray okay, which follows this one. Okay, and remember that this angle must be always smaller than this angle. The eye over here is always smaller than R because it's going from the water to the air. Okay, diagram 6. Let's go to question number 6. Shows a satellite orbiting the Earth. State Newton's universal law of gravitation. Okay, it's a very, very long law. Okay, and then you have this much space to write in. So I'm just going to give you the basics. Of course, you need to know the full sentence. Okay, the force between two objects, or the gravitational force between two objects, is directly proportional to the product of the masses. Okay, and it's inversely proportional to the square of the distance between both objects. Okay, it's a very, very long law, but it is directly proportional to something and is inversely proportional to something else. Okay, and so this is what I mean when I say you can, in paper 2, especially, you can only use directly inversely proportional when you're talking about law. If the law says it, if a principle says it, if hukum okay, if it is a definition that memang in the definition it says inversely directly proportional, then you can use it. But when you're stating a relationship like the one that we saw just now, please don't use the words directly inversely proportional because there's no graph. Okay, you're just looking at the numbers and you're making the relationship based on the numbers. So be very careful with that. Okay, if the altitude of the satellite around the Earth is 550 kilometers, okay, and the linear speed is 5.48 times 10 to the power 3, and then you're given all these constants lah. Okay, what is the centripetal acceleration? Okay, centripetal acceleration formula is v squared over r. Okay, v is given over here. Now the r, you need to be very careful. R is always from center to center. Okay, so the altitude of the satellite is 550 kilometers, but they are giving you the radius of the Earth as well. So when you're talking about the R, okay, let's say this is the Earth and this is the satellite. Okay, the R is always this whole thing. 550 is only here. This is the radius of the Earth. So it needs to be added together. So be very careful with this. Okay, 5.48 times 10 to the power 3 over 550 times 10 to the power 3. Why? Because I'm changing kilometers to meters. Plus 6.37 times 10 to the power of 6. Okay, so then you will get the answer 4.34 meters per second squared. Okay, please bear in mind, everybody, this calculation is usually where people get things wrong. Okay, they always somehow calculate things wrongly, so make sure you know how to calculate until you get the correct answer. Okay, the next question is determine the gravitational acceleration at the position of the satellite. So the formula for gravitational acceleration is G equals to big G times mass over R squared. Okay, once more, everybody, the R is very important here. Okay, if we're going to follow this one, it will be 6.67 times 10 to the negative 11 times 5.97 times 10 to the power 34. Okay, which is 24. 24. Okay, over. Now, once again, be careful. This is 550 times 10 to the power 3 plus 6.37 times 10 to the power 6, the whole thing squared. Okay, so there's an additional of the squared over here. Okay, so please make sure that you know how to use a calculator to calculate this and make sure that you don't make any mistakes in the calculating. Okay, so you get the answer of about 8.315 meters per second squared. Okay, now calculate the escape velocity. Escape velocity formula is V equals to 2gm over r. The whole thing is square root. Okay, so again, I cannot emphasize the importance of this r over here. Okay, but I'm not going to write it down because everything is already written down. The answer you get is about 10727.83 meters per second. Okay, or about 10.73 kilometers per second. Now, the reason why I changed to kilometers is because of this question. Based on your answer in 6B1, can the satellite overcome the gravitational force of the Earth if the satellite is launched at a speed of 9.8 kilometers per second? Okay, so basically it's asking, can it overcome the the escape velocity lah? Okay, when you compare this value, this 9.8 and this is 10.73, so obviously the answer will be no. Okay, because it hasn't reached the escape velocity, so it can't leave the Earth yet lah. Okay, so that's it. Okay, diagram 7.1 shows a typical generator, okay, connected to a galvanometer. So state Faraday's law. So Faraday's law states that the induced EMF, okay, is directly proportional, okay, to the rate of change of magnetic flux. Okay, that's the standard definition lah. The rate, rate of change of magnetic flux. Okay, then what are components A and B? Okay, if you take a look here, this is obviously an AC generator because it has these two things. So A is the slip ring and B is the carbon brush lah. Okay, so A is slip ring, B is carbon brush. Okay, what will happen to the galvanometer if a stronger component C is used? So if you take a look, component C is the magnet. Okay, so if you use a stronger magnet, obviously there'll be a bigger current flow, lah. Okay, because of Faraday's law. So what will happen to the galvanometer? Okay, there will be a bigger deflection. Okay, dia akan lebih terpesong. Okay, so from diagram 7.1, state the type of current. So this will be alternating current. Okay, or AC, because of the slip rings. Okay, so based on the answer in 7C, okay, explain clearly on how the current is generated. So, since this is only 1 mark, and I suppose they are asking for how do you produce a bigger current lah. Okay, so there'll be more cutting of magnetic flux produces a bigger induced EMF. Okay, because C is bigger deflection. Okay, if component A is replaced with commutators. Okay, so when you see the word commutator, you know that the type of current will be direct current. Okay, otherwise known as DC. Okay, now draw the signal patterns that differentiate the direct current and the alternating current. Okay, if I change the galvanometer to the oscilloscope. Okay, so direct current, most important one is they must be in one direction. Okay, and alternating current will be changing direction. Okay, yeah, you can forgive the you can forgive the size lah, but the most important thing is direct current is always one direction. Okay, alternating current is one way and then the other way, one way and then the other way. Okay, explain how the direct current is produced from the generator, which involves the flux magnet. So there's 2 marks lah. So of course, when you're talking about production of current, you always have to talk about cutting of magnetic flux. Okay, but of course, since there's 2 marks, I think you have to differentiate also between the difference between alternating and the direct current, which is the commutator. Okay, so the first point will be the cutting of magnetic flux produces an induced EMF. Okay, that's 1. Induced EMF, which then of course produces the induced current lah. Okay, then of course the second one you talk about the role of the commutator. Okay, so the commutator, okay, ensures the current flows in one direction only. Okay, so because this is the difference between alternating and direct current. Okay, direct current involves a commutator. Then make sure it only flows in one direction only. Okay, diagram 8 shows a load hung on 2 identical springs. Okay, state Hooke's law. Hooke's law, okay, another indirectly proportional. Okay, the force is directly proportional to the extension. Okay, but there is a syarat, there's a condition for this. Okay, if the elastic limit is not exceeded. Okay, as long as the spring or the wire or any material that is being applied the force, okay, the extension will be directly proportional to force, but the elastic limit cannot be exceeded. Okay, if the mass of the load is 4 kilograms and the extension is 40 cm, okay, calculate the spring constant. So the formula that is involved here is F equals to Kx. But please bear in mind that this X over here needs to be in meters. Okay, so you want to make sure that you change it into meters. So the load is 4 kilograms, which is the weight. Okay, so if it is 4 kilograms, then the load will be 4 times 9.81. Okay, now the extension of the spring is 40 cm, but there are two springs here. Okay, so if the extension, if they extend until 40 cm, which means that the load the burden has been shared between the two, since this is a parallel arrangement. So the actual extension, okay, the actual extension, if it is just one spring, okay, the actual extension will be 80 cm. Okay, because 40 cm is already divided by 2. So if you just put one spring there, it will extend up to 80 cm, which you change it to meters to be 0.8. So this will be K times 0.8. Okay, so you will get the K is equals to 49.05 Newton per meter. Okay. Then you calculate the elastic potential energy if one spring with 55 cm extension. So let's change it again. 55 cm is 0.55 meters. Now, formula for elastic potential energy is 1 over 2 kx squared. Okay, and you already have the k, 49.05. Then the x is 0.55 squared. Okay, so you will get divided by 2 times 0.55 squared. Okay, you get about 7.4 2 joules. Okay, because, yeah, 7.42 joules. So be very careful when it comes to Hooke's law, okay, especially if you're talking about parallel or series arrangement of springs. Okay, the extension okay, given may not necessarily be referring to just one spring. Okay, it can be actually referring to more than one. Okay, let's carry on. So table 1 shows 4 models of spring cradles. Okay, you have all this. So based on the information, state the characteristics of spring cradle that are suitable to be used for a baby. Okay, so of course, the type of, if we analyze, okay, we want to use for baby, right? So obviously we want a stainless steel. Okay, we don't want wood. I've never seen a wooden spring, but okay, fine. But basically wooden, okay. Anyway, the diameter, okay, the diameter should be small. Okay, diameter of the spring coil, okay, should be small. And then of course you want it to be in parallel, okay, so that the extension won't be too much. So obviously the best choice would be P once you've done the analysis. Okay, so the type of spring material will be stainless steel. Okay, and usually stainless steel will be last longer because of the word stainless okay, or avoid rusting. Okay, these are the two usually good ones Okay, the diameter of the spring coil will be smaller. Okay, and then why? Because we want a bigger spring constant, or the friend to bigger spring constant is the word stiffer. Okay, a stiffer spring Okay, not too stiff but it's just one more stiffer than normal Okay, the arrangement of the spring should be parallel. Okay, and all this leads to the same reason. Okay, which is a bigger spring constant. Okay, or stiffer. Okay, and again, everybody, when you think about stiffness or you want to think about smaller spring coil, please don't go to the extremes of thinking like this super small, okay? Smaller and bigger is always relative. We don't want a super huge spring because that will make it very soft. Okay, but we don't have super small one. When we talk about smaller means, small than big, smaller than big. And then when we talk about stiffer, we're talking about, yes, it can still bounce okay? It's just a little bit more difficult to bounce than normal. Don't think about stiffer, wow, means a stiffer spring, means very, very keras, like that's very extreme. Don't think about it in such extremes. Okay, especially when it comes to spring. Sometimes students tend to think in terms of extremes, which is quite funny when you think about it. Okay, but we hold on to the fact that the smaller diameter parallel arrangement always ends up for a stiffer spring. And a stiffer spring, a stiffer spring system is definitely better than a not stiff one. If it's super elastic, okay, then the poor baby cannot sleep. He'll be having too much fun, okay, bouncing up and down. So the best answer for this will be P. Okay, when you talk about this one. Okay, now let's move on to the three questions in section B and section C. Let's come to section question 9 now. Okay, so because of the lack of space, I'm just going to show you the questions on this side. Okay, but it's very small. And then of course on the left side will be what the answers are. Okay, so you have Arman putting 2 cubes of ice in a cup of hot coffee, as shown in diagram 9.1. He preferred iced coffee. However, he unintentionally left the coffee out for a long time. The ding dong. Okay, fine. So what is the meaning of thermal equilibrium? So thermal equilibrium is a situation. Okay, so when 2 objects are in thermal. Okay, the first keyword is the word thermal contact. Okay, when 2 objects are in thermal contact, the net heat flow is 0, second point. Okay, and they they have the same temperature. Okay, so this is the situation where something is in thermal equilibrium, or an object or 2 objects are in thermal equilibrium. Okay, so 2 objects are in thermal contact, they have to be touching one another thermally. And of course, the net heat flow is 0, or net heat transfer is 0, and then they have the same temperature. Okay, so explain the flow of heat between the ice and the coffee until thermal equilibrium is reached. And if you notice here, it is a 3-mark question. Okay, so the first thing you need to know is that there is heat flow, okay, between the ice and coffee, which means that there is heat flowing from the ice to the coffee and heat flowing from the coffee to the ice. We must never make the mistake that heat flows only one way. Okay, when 2 things are in thermal contact, heat flows always 2 ways. The only difference is more heat flows. Okay, think about it. Who is hotter? Obviously, it's the coffee lah. So more heat flows from the coffee to the ice. Okay, or vice versa. Less heat flow from the coffee to the ice. Okay, and then of course, then you can talk about how thermal equilibrium is reached. Okay, thermal equilibrium is reached, okay, when the heat flow between ice and coffee is at the same rate. Okay, or if you want to use another word, you will have the net heat flow. Okay, is 0. Either one of these is totally fine. Okay, so the most important thing to remember when you're talking about this is that heat flows 2 ways. It's never flowing one way. Of course, when if you think about it logically, one has to flow more heat. The hotter object has more heat to flow out than the colder object. But by and by, it gets less and less and less until the heat flow becomes the same rate, or the net heat flow is 0. Okay, then you have radiator. Okay, so the car radiator, remember the function of the car radiator is to cool down the car engine. And how does it cool down the car engine? It does it by taking away the heat from the engine. Okay, so you want to make sure that you have this in mind. Okay, so when we talk about the number of strips, okay, obviously we want to have more. Okay, we want to have more strips so that more heat can be dissipated out. Okay, the size of the fan must be big. The purpose of the fan is to suck out the heat, okay, from the water. Okay, the boiling point has to be a higher boiling point, And then, of course, the specific heat capacity has to be as high as possible so that it doesn't get hot too often. So when you look at it, obviously, C is the best answer lah. Okay, so coming back to this. So when we answer, of course, we answer in table form. Okay, so the number of fan blades is, yeah. Okay. The number of fan blades is more. Okay, or more number, okay, also can. Okay, so the reason will be more heat can be dissipated. Okay, the size of the fan is big size. Okay, for the same reason, okay, more heat can be dissipated. Or if you want to use another one, okay, it can suck out more hot air. Okay, remember the purpose of the fan is to suck out all the hot air from the water. Okay, so that the water can, so that the water can return to the other part of the radiator and bring in more heat. Okay, this is what I want to mention because based on our trial exam, I noticed that there are still a lot of people who are doing this very rookie mistake. Yes, I want the answer to be 100 degrees Celsius. There are only two choices. It's either 78 degrees Celsius or 100 degrees Celsius. Okay, but we have learned, okay, from other people that whenever you answer a question like this, the value is no, don't mention the value. Okay, so the boiling point of the cooling liquid is high. I don't want 100 degrees Celsius. Okay, it should be either higher or lower. Okay, for some reason or another, this is a technicality lah. Okay, which you need to pay attention to. If you write 100 degrees Celsius, there is a very high chance that your answer will be wrong. Okay, even if you're on the right track, okay, you will not get the mark for it. Okay, why? It's a technical thing. I can't really explain why. Okay, so the boiling point of the liquid is high. Okay, so we want it to be high so that it will be avoid evaporation. Because remember that the car engine is very hot. If it reaches 100 degrees Celsius, it will probably boil the water. So we don't want the water to be boiled away lah. Okay, to avoid evaporation or to avoid the boiling of the liquid. Okay, which is something we don't want. Okay, specific heat capacity, again, we have two choices, either a low specific heat capacity, 2450, or a high specific heat capacity, which is 4200. So we want the specific high heat capacity to be high. Okay, and specific heat capacity high usually comes with a set answer lah, is that it is able to absorb more heat before rising in temperature. Okay, able to absorb more heat before rising in temperature. So if it is a low specific capacity, you just need a little bit of heat, then it can rise temperature if you don't want that. Because remember, the car radiator is usually very hot. Okay, so of course, the last 2 marks will be C is chosen. Okay, and why? Why is you write all these 4 things again lah. The number of fan blades is more, the size of fan is big, the boiling point of cooling liquid is high, and the specific heat capacity is high. Don't need to write the ones on the right, you just write the ones that are on the left. Okay, so let me show you. The number of fin blades is more. Okay, second point, the size of a fan is big. The boiling point is high. The specific heat capacity is high. Okay, make sure you have all these 4 points in order to get that 10th and final mark. Okay, so usually people will miss this out, or they will do everything and then they will write everything that is on the right. No, please. Okay, everything that's on the left over here, just transfer over. Oh, sorry. Okay, all this transfer over here. Okay, in order to get that 10th and final mark. Okay, let's carry on. Okay, so then the next question is, other than that, okay, suggest another factor that can increase this one lah. Okay. When I was researching for this, I find that it's so funny that suggests other factors. I guess it suggests another modification or put another suggestion lah. Okay, so my answer will be to include a thermostat, which is usually what you find in cars lah. Okay, include a thermostat, and the reason for this would be to monitor the temperature, okay, of the coolant, or to avoid overheating of the radiator, which is what we want to avoid. Okay, because if the radiator is overheating, it's a very, very big problem for us. Okay, question C. Ali shares a large amount of water in the concrete tank, okay, as preparation for drought. Okay, at night, he notices that the water is warmer than the tank, while at noon, the water is colder, okay, than the tank. So this is very similar to the beach, the sand and the sea, okay, at day and at night. So explain the situation by using the concept of specific heat capacity between the concrete tank, yeah, okay, and the water. So let's explain this. So the specific heat capacity, okay, of the tank is smaller. Okay, so if the specific heat capacity of the tank is smaller, therefore it is easier to get hotter and also easier to get colder. Okay, so it heats up easily, or no, actually not easily. Let's not use the word easily. It heats up faster. Okay, in the noon, and cools down faster at night. Okay. So then you write the opposite for water, because just now you're talking about tank, now you're talking about water. Okay, so the specific heat capacity of water is bigger. Okay, and so if the specific capacity of water is bigger, so it heats up slower in the noon and cools down slower at night. Okay, that's why it feels warmer at night. Okay, and it feels hotter in the noon time lah. Okay, because it takes a very, very sorry, it feels cooler in the noon because it takes a very long time to get hot. Okay, let's go to the second question. A small amount of water is transferred into a bucket. Okay, compare the temperature of the water in the bucket, okay, and the concrete tank at noon. Now, in the normal situation, okay, it says here that at noon, okay, the water is colder than the tank. Means the tank is much hotter compared to the water because it takes a very long time to heat up. But now you're taking the water out and putting it to a small bucket, then you want to compare it to the tank. Okay, so when you want to compare the temperature of the water in the bucket, obviously the temperature of water in the bucket will be higher than the tank. Okay, now why is this so? Okay, if we go back to the formula for heat, Q equals to mc delta theta. So now what we're interested in is this delta theta. Okay, so the delta theta is equals to Q over mc. Okay, and so the amount of heat, it kind of doesn't change because it's noon. It's the same amount of heat for both the tank and also the water in the bucket. But now our mass is greatly, greatly reduced compared to the water in the tank. Okay, so since our mass has been reduced, okay, the specific capacity doesn't change. So since the mass has been reduced, the temperature change must be very high. Means it gets hotter faster because there's less water already now. Okay, so uh if there was a second mark for this, I think there must be because it's 2 marks. So the second mark will probably be an explanation, and how I would explain this will be the reduction of mass. Okay, reduced mass, okay, leads to a higher temperature change. Okay, is how I would answer this question. Okay, for 2 marks lah. Number one is you make the comparison, and number two, although they didn't ask you to explain, but I guess you should anyway because it's 2 marks. And you talk about less mass means higher temperature change. Okay, compared to when the water was in the tank. Okay, there's a lot of water lah, I suppose. Okay, so the tank doesn't change, but now you're changing the amount of water. So the water in the bucket is much less mass, so there will be a much higher temperature change. Okay, let's continue on to question number 10. So diagram 10.1 shows a typical commercial airplane flying in the air, even though its total weight is very heavy. Okay, so what is the principle of physics? Okay, that explains how objects heavier than air are able to fly. This is Bernoulli's principle. Okay, please bear in mind that the spelling of Bernoulli cannot be wrong. Okay, so explain the mechanism which plays an important role in enabling the aeroplane to fly. So this is 3 marks. Okay, so of course you talk about the shape of the airplane, the airplane wing. Okay, the wing of aeroplane, okay, is in aerofoil shape. Okay, don't worry about the English now. The wing of the aerofoil is aerofoil shape. Okay, then you talk about above the wing. Okay, so let's talk about the aerofoil shape. So you talk about the region above the wing and the region under the wing. Okay, so above the wing, okay, air speed is higher. Therefore, creating a low pressure region. Okay, and then the next one will be under the wing is the total opposite lah. Okay, air speed is lower. Okay, therefore creating a high pressure region. Okay, and then of course the fourth and final point. Yes, I know it's only 3 marks, but you should also mention this lah. Okay, the fourth and final point is the difference in pressure. Okay, which is probably the most important word when you're talking about Bernoulli's principle. The difference in pressure, okay, creates a lift force. Upward, obviously upward kan. Okay, a lift force upward on the wing. And that's how the airplane is able to fly. Okay, let's continue. So the next question is Bunsen burner. Okay, so you're required to study the characteristics, etc., etc. Okay, so when we analyze it, first we want the size of the air hole to be big lah. Okay, obviously we want a big air hole so that more oxygen or more air can come in. Okay, the size of the nozzle. Okay, I'm assuming okay, that the nozzle is the one that that is in here. Okay, the one in here. Okay, the nozzle where the gas will come out. So when we want the gas nozzle, we want it to be small. Small means high velocity, low pressure, and therefore the air from the outside can come in. Okay, the size of the base. Okay, this is it's a very easy question. Base has to be big so that you have more stability. And then of course the type of collar must be a movable collar lah. Okay, because if you have a movable collar, then you can adjust the amount of air, okay, that is coming in. So just like the question just now, okay, the size of the air hole, sorry, why did I write air blade? Sorry, air hole. Okay, size of the air hole is bigger. Okay. So air hole, so more air can be used for combustion. Okay, combustion. Okay, the size of the nozzle is small. Okay, and why? And so if the size of the nozzle is small, it will create a low pressure region. Okay, so that air from the outside, okay, can be pushed in. Okay, I feel like we've answered this question before, but never mind. Okay, the size of the base is big. Oh, sorry, it's not big, it's wide. Okay, the size of the base is wide, so more stable, okay, or to increase the stability. Either one is can. The type of collar is the movable collar. Okay, and then the reason is, okay, either to control airflow, okay, or to control the heat of the flame. Okay, so the collar can be moved, means you can pushing, so that you can have less air, more air. Okay, remember if you have more air, then you have complete combustion, etc., etc. Okay, so the best, so K is chosen. Okay, and then don't forget to write the 4 points, 1, 2, 3, 4. Just transfer everything from the left-hand side of the table into this part. Okay, make sure that all 4 points are written in order for you to get that full mark. Okay, but once again, we have this question. Apart from the condition given in table 3, suggest another factor that can be included into designing the Bunsen burner. Okay, so I did a little bit of research on this. So maybe it's not shown in this picture, so I guess that's why we can put this in lah. Okay, so include a gas valve. Okay, a gas valve is the one where you use to control the amount of gas lah. Okay, so the reason for it to be to control the gas flow. Okay, if you have too much gas, then you have a lot of burning happening lah. Okay, if you have less gas, then there'll be less things to burn. So it depends on the situation where which one you want. You want more gas, you want bigger fire, you want smaller fire. So a few things contribute to all this lah. Okay, not just the air hole, not just the collar, but also the size of the valve, and also the gas valve itself. Okay, so this will be how I would answer this. And then of course you have the final question, which is this one. Okay, so a roof in a warehouse, okay, has a mass of 30,000 kilograms, okay, and a total surface area of 150 meters squared. Okay, so during a hurricane, the wind produces a difference in pressure between the upper part and the lower part of the roof of about 3,500 pascals. Okay, so the difference in pressure is 3,500 pascals. This causes the warehouse roof to be lifted. Okay, so first of all, find the weight of the roof. So the weight of the roof is very easy. Okay, which is 30,000 kilograms times 9.81, which is about 294,300. Okay, newtons. That's the weight of the roof. Okay, now find the net force acting on the roof. Okay, so first of all, we need to know what is the lift force. So the lift force comes from the original pressure formula, which is P equals to F over A. If you have a pressure of 3,500 pascals, Our F is here, and our A is 150 meters squared. Our lift force is 525,000 newtons. Okay, so the lift force is 525,000 newtons, but there's a weight of 294,300 newtons. So the net force, sorry, this is the lift force. So the net force is the lift force minus the weight, okay, which is 525,000 minus 294,300, which will give you 230,700 newtons. Okay, 230,700 newtons, which is the answer to this. Okay, so quite interesting. This question is a very interesting question. Never seen it asked this way before. It's definitely a very interesting question. Okay, we come to the final question, finally. So diagram 11.1 shows a transistor circuit used as a current amplifier. Okay, name the type of transistor. Since the arrow is going downwards, this would be an NPN. Okay, transistor. Okay, so the second question is, explain how the transistor circuit acts as a current amplifier. Okay, so you have to first talk about how the transistor gets switched on, and then of course how the collector current becomes much bigger than the base current. Base current is in microampere, okay, if you notice over here, okay, whereas the collector current is in milliampere, which is much bigger. Okay, so the first thing you have to point out is small base current flows, okay, in the base circuit. Okay, that's the first point. Now, when the small base current flows, okay, the transistor is switched on. Okay, and allows collector current. Okay, IC, sorry, this base current is IB lah. Okay, to flow. And then since we're talking about current amplifier, okay, the amplification is calculated using IC over IB. This will be the 3 points. Basically is, how do you turn on the circuit? How do you turn on the transistor? You turn on the transistor by putting a small base current. When the transistor gets switched on, it will allow the collector current to flow. Then you can calculate the amplification or the current amplifier, which is IC over IB. So the third question, calculate the current amplification if the net changes of IB is 50 microampere and the net changes, so finally, of IB is 5. Okay, 5 microamperes. Both also is micro lah. Okay, sorry. IC is 50 and IB is 5. So the amplification will be IC over IB, which is 50 micro over 5 micro. Not too bad lah, because both is micro, so you can saling this one. So you get 10. Okay, and amplification, no unit. Okay, B. Shows an arrangement of 4 diodes that form a bridge rectifier. So based on 11.2, describe the process, okay, that allows the current to flow in a complete circuit in the same direction. So first of all, you have to name the process. Okay, the process is process of full wave rectification. Okay, so full wave rectification, remember in an AC current, there's always the positive cycle and then the negative cycle. Okay, so when it is the positive cycle, if it is flowing this way, notice that these two are forward bias. Okay, these two are reverse bias. But when we change the other direction, okay, if it is flowing this way, then this two is forward bias, this two is reverse bias. Okay, so that's how you would describe the process lah. So first of all, in the positive half cycle, okay, D1 and D2, which is this one, Sorry. Okay, D1 and D2, okay, are forward bias. Okay, and then current, okay, current flows from top of resistor to bottom, okay, which is from here to here lah. Okay, then the second one is the negative half cycle, which is the green color one. Okay, negative half cycle, D3 and D4 are forward bias. Okay, and we find that because of that, the current flows in the same direction. Okay, the current flows in the same direction, which is also from the top to the bottom. Okay, because of how they are biased now. I hope I'm reading this number correctly though. Yeah, the first half cycle is D1 and D2, and then the second half cycle is D3 and D4. Okay, which is both of these are forward bias lah. Okay, so this changes alternating current to direct current. Okay, which is what is called full wave rectification. Okay, all right. I think this is our final question. Okay, diagram 11.3 shows a transistor-based circuit which is used as a light control switch. Okay, the circuit consists of resistors A and B, light emitting diode LED, which is C. Okay, a light dependent resistor LDR, which is D, and then the transistor E and the 6-volt battery F. Okay, now an engineer was required to make some modifications based on the circuit diagram 11.3 to build an automatic water sprinkler during hot temperature. Okay, so obviously our circuit now is wrong lah, because this is an LED to show light and this is a light dependent resistor. So this is turn on the light when it is dark. Okay, so we don't want that. Now we want a water sprinkler in order to and then of course we need a temperature sensor lah. Okay, so using knowledge of electronics, explain the modification of the component, the position of the components, and the components added into the circuit. Okay, wow, there's so many. Okay, so the first and most obvious one is we have to change this. Okay, this is a LDR, which we don't want, a light dependent resistor. So we want to change it to a thermistor, because a thermistor is the one that controls the that changes the temperature. So the first one is change LDR to a thermistor. Okay, and the reason for this is to detect changes in temperature, because that's what we want. Okay, so that's the first one. Okay, then the second one is, of course, the positioning of the LDR, has to change. Sorry, the thermistor, the thermistor must be on top. Okay, so change resistor A and D. Sorry, change the positions. Okay, of resistor A and D. Okay, because, and the reason for this is the thermistor has low, not high. Okay, low resistance at high temperatures. Okay, so if this one has low resistance, then this one will be high resistance lah. If this is high resistance, there will be current flow. Okay, and that's the basic thing of a transistor circuit. Whatever that happens at the base must have high voltage. High voltage means high resistance. Sorry, high resistance means high voltage. High voltage means there will be current flow. If got current flow, then IC will flow lah. Okay, so that's why we have to have a low resistance at the top during high temperatures, because we want the sprinkler to turn on during high temperatures. Okay, another possible reason you can put for this, you know what, let me rub this off first. Another possible reason, if you don't want to use that reason, is the sprinkler, okay, can turn on during hot temperatures, which is the reason that was given in the question earlier lah. Okay, the sprinkler can turn on during hot temperatures. Lana, it's a little bit of a lag. Okay. Now, the third thing that we need to know is, of course, we have to change this one lah. Okay, the LED, because the LED is pointless. We want a sprinkler system. So change the LED to a sprinkler system. Okay, of course, that's the most natural one lah. Okay, so change the LED to a sprinkler system. Well, the reason is because you want to build a sprinkler system, kan? Okay, so, well, I guess you can use the same reason lah. Okay, the sprinkler can turn on during high temperatures. Okay. And then, okay, because we're talking about sprinkler system, and it's, you know, a system is very different from an LED. LED is just one light. And usually when we have a system like a fire alarm system or a sprinkler system, it requires more than just 6 volts lah. Okay, and so you need to add what we call a relay switch circuit. Okay, add a relay switch, okay, circuit to the sprinkler system. Okay, and the reason for this, the reason why you add a relay switch is the sprinkler system requires higher voltage to function. Okay, 6 volts is not enough. 6 volts is enough for the LED. It's also just one LED. This is the entire system altogether. So you need to add a relay switch that is connected to, you know, a bigger power source lah. Okay, which is definitely higher than 6 volts. Okay, and then finally, okay, you use a bigger resistance for B. Okay, for resistor B, which is, gosh, it's gone already. The resistor B, this one lah. Okay, yeah, resistor B is that one. And so we use a bigger resistance for B, okay, usually is to control the current flow. Okay, control the current flow or to prevent the transistor from damage. This one is a very normal reason lah. Okay, when we usually use a bigger resistance for B, because the purpose of this particular resistor over here is to control the current flow so that the transistor doesn't get damaged. Transistor is an electronic component, so it's very, very sensitive. Okay, if you have too much current flow, then it will spoil, which we don't want it to lah. That's why we have a much bigger resistor. And now, of course, we're talking about a sprinkler system. Definitely you need much more of a controlled current flow. Because if too much current flow, then, you know, it's a very big problem. But it needs to be able to still switch on the transistor lah. Okay. I guess that this question number 11, is probably the most challenging of all the 11 questions there are. So, you know, take your time. Pause if you want to, take a break if you need to. Don't be in a rush to understand this. Okay, but if you have any questions, please feel free to ask me. Okay, and I'll see you in the next video. All right, take care, everyone.